I guess I'd like to begin by thanking you students collectively for all your questions. You know, I realize that this is a field that's very different from I think what any of you work in, and I just really appreciate your intellectual curiosity and openness to ideas. And I think if you can keep that with you, it goes a long way to a happy life in science. That's my claim. So what is the plan for today? I've written it up here. So we got most of the way to deriving a transport equation for cosmic rays in the limit of frequent scattering. This is called the Parker equation. It was written down with little formal justification in 1965. Then other people came and kind of backfilled. And even though that's a long time ago, it's still used, and the statute of limitations does not apply. If you want to work in this field, it's something that you have to learn. And once we have it, we're very close, then we'll derive an energy equation, which would be suitable for substitution into fluid models. Then we'll use very similar machinery to write down an alternative transport equation, which is based on the theory that the fluctuations which are responsible for all the scattering are actually excited by the cosmic rays themselves through a kind of mutual regulation process. And that will lead to a very similar but different energy equation. And then I'll show you some slides in which these theories are applied to various astrophysical problems. And you'll see that their predictions are really quite different. And so again, it's really important to get this right. And then that'll be it. And I also want to apologize in advance for not being at the session this afternoon, but it's actually not that easy to get to Madison, Wisconsin. And so I will be leaving for the airport. Did not have a lot of choice. Okay, so we had started with Vlasov or Boltzmann equation. And so that was partial F, partial T, plus UV, partial F, partial S, equals, so here's our scattering term, d by d mu, nu times 1 minus mu squared over 2, partial F, partial mu. And we had solved this order by order. We had derived an expression for the anisotropy. Partial F, partial mu is minus V over nu, partial F, partial S. We had subscripted this with a 1 and a 0, and we had derived diffusivity, kappa, which turned out to be the integral minus 1 to 1 of V squared times 1 minus mu squared over nu d mu. That was our spatial diffusivity. And we were up to considering, what if the fluctuations that scatter are moving with the fluid. Which let's write in this way. So the cartoon that we should have in mind is this. So here's our field line, and I'm going to draw 2 sets of fluctuations on it. So here we're moving with a speed u of s plus delta s. And here, we're moving with a speed u of s. Okay, so now we have a particle, and it comes along, and it reflects off this fluctuation. So most of the scatterings are small angle, but we can derive the effect that we want by considering this kind of extreme limit of reflections. Okay, so there's a change. Delta, I think I've been using small deltas, delta P parallel is, well, it's the cosmic ray came in, so it overtook the fluctuation and then it scattered back. So it's losing some parallel momentum, and the amount of parallel momentum it's losing is minus 2 P parallel, minus 2, its mass times its Lorentz factor times u of s plus delta s. So this is the particle mass and Lorentz factor. Okay, so it's lost some parallel momentum. Now it goes all the way back and it reflects off this one again, and delta P parallel now, so now it hit head on, so it gains some momentum. It's plus 2 m gamma u of s. And I'm going to leave gamma the same for simplicity, assuming that the change is very small. I'm sort of protected in this derivation by none other than Enrico Fermi himself, who was the first one who came up with it. So I'm in the shadow of a giant. Okay, so the net P parallel per loop is 2 m gamma u of s minus u of s plus delta s, which we can do a Taylor expansion here, is minus 2 m gamma delta s du ds. Okay, so if the velocities were the same, then the whole process would be elastic, but they're different, so there's this change. Okay, now how long does it take to make a loop? So the time to complete the loop, it goes there, back, and there again. It's about 2 delta s over v parallel. This is now v parallel for the particle. Let's call this delta t. So dp parallel by dt is approximately delta p parallel over delta t, which is minus 2 m gamma delta s du ds divided by 2 delta s v parallel. So the delta s's cancel, the 2's cancel, and this is minus P parallel du by ds. Okay, so if du ds is negative, namely a converging flow, the particle will gain energy, and if the flow is expanding, the particle will lose energy. And since the motion is three-dimensional, not one-dimensional, there should be, so if we average over all particles, we should count for angular averaging. Okay, so is the physical origin of this effect clear? Silence. Silence is consent. Okay, but ask questions at any time. Okay, so we are now going to put this into our Parker transport equation. Okay. So partial F, partial T plus U. Now, I'm now going to write this in vector notation rather than d by ds, which is the way it's traditionally presented. U dot grad F. Now, I'm going to consult my notes because it is so important to get the sign of this term right. I don't trust myself. Okay. So this is the derivative, or it's the convective derivative. So the idea here is that the cosmic rays are sort of carried by the fluid, equals, well, our spatial diffusion term so we talked about the spatial diffusion term, and then we incorporate this term as P over 3, divergence of U df dp. So this represents, we can think of this as dp dt dot partial f partial p, which is, so in a sense, this term has replaced the Lorentz force that was here way back when we wrote down the original Vlasov equation, and then plus a term I'll just write as S, which represents sources and sinks. Okay, so Parker, as far as anyone can see, wrote this equation down, really based on physical intuition, not on an elaborate derivation. And this has been a semi-elaborate derivation, so this is a good time to ask if you have any questions about it. Yeah. This one here. So if you go into, if you make a transformation to a frame moving with the fluid, and then just say that the particle has changed direction and transformed back, this is what you get. Yeah. For these particles. So gamma is, so the rest mass of a proton is about 1 giga electron volt. And we're interested in primarily in, several to a few tens. So gamma would be probably like 3 to 100 or something. Pretty close to the speed of light. And that's why I'm going to make the ultra relativistic approximation. Yeah. Yeah, that's a great question. So as I think I mentioned in the first lecture, electrons are down from nuclei in cosmic rays by a factor of about 50 to 100. And the sort of general explanation for this is that during the acceleration process, acceleration has to, or transport for that reason, matter, has to compete with radiative losses, including inverse Compton. So in intergalactic space, it's mostly the cosmic microwave background. In galaxies, just local infrared radiation plays a big role. Synchrotron radiation too, they're both important. For ions, we can generally neglect them unless we're in intergalactic space and we're at very high energies. We are not considering them, but if you wanted to consider them, you would put them into this term. Okay, so this term really covers a multitude of sins, and I'll actually use that term. So I'm going to give, at the end of this, I'm going to give a little analytical example of sort of how convection and diffusion play out in a simple system with a delta function source. Okay, so here we are. So now let's finally get our energy equation. So we're going to take our transport equation, partial F partial T plus U dot grad F, right, this is U gas here, equals divergence of U P over 3 dF dP plus divergence of kappa dot grad F plus this general source and sink term. And we're going to multiply the whole thing by particle energy and integrate it over phase space. Let's just write D3. Okay. So let's define a new symbol. Lowercase uc will be the cosmic ray energy density and in the ultra relativistic approximation, the cosmic ray pressure is 1/3 of UC. I'll use that sometimes. Okay, so this term is just partial T. We can take the partial T outside, and then we just get UC. So the time rate of change of UC. And we can do the same thing here. UG doesn't depend on momentum, so we take that outside the integral, and we get another UC. So this is the rate at which UC is advected. And now we come to this. Okay, so divergence of U over 3, energy, momentum over 3, dF dP, P squared dp d mu. Okay, so this is the term we're going to have to work on. And then here, so this is the spatial diffusivity. It depends on the scattering frequency. That can be a function of momentum. So we have to define an appropriate mean. So I'm going to call that, it's the energy diffusivity. We can go into how that's defined, but we're just going to leave it as kappa E for now. And then let's write this as the energy sources and sinks. Okay, so everything is in a fairly transparent form except this. So I'm going to follow Steve's lead and call this a pain in the neck term. This is the pin term. Stay clean. And so let's work on that. So this is a lot less painful actually than Steve's. Say what? Oh, this is D3P. Oh, because I made a mistake. Thank you. Okay. Okay, so now the PIN term, div u over 3 integral of P. So we had P df dp and then P squared. So P cubed, energy per particle, df dp, dp d mu. Okay, so we're going to integrate that by parts. So we're going to pick up a minus sign, divergence, I'm calling this UG. So now we move the derivative over to P cubed E. df dp, dp d mu. And now we use, so this is actually relativistically correct. dEdp is V, the particle V. So our term becomes minus divergence of UG over 3 integral. Okay, well, we have an energy density, and then we have d by dp of p cubed. So that's 3 p squared. And then we have a v p cubed. And then we have an f d p d mu. Okay, well, so this is just our energy density integral. So that's minus the divergence of UG over 3. And then we have a factor of 3 here. So this is 3 UC. And then we have V P cubed over 3. We recognize that as pressure. So now we have pressure, or 3 times the pressure because we kept the 3 outside. So the pain in the neck term turns out to be factors of 3 cancel, of course, minus the divergence of UG times UC plus PC. Okay, so now we have everything. So I'm going to rearrange things a little bit. Partial T of UC is minus UG dot grad UC minus the divergence of UG times UC plus PC plus an energy diffusion term plus our source and sink term. So I think it's useful to write this in a slightly different way. So let me do that. So I'm going to write this as minus the divergence of UG. And now I'm going to add an extra PC here. UC plus PC. And then I wasn't really supposed to do that, so I'll add this term back on. UG dot grad, it's more capital looking, PC plus divergence of kappa E dot grad C plus S. Okay, any thermodynamics or fluid dynamics mavens here who recognize what this term is? It's very close. It's very close. This is actually, so this represents the work done on the fluid by the cosmic rays. And how about this? This is the divergence of the enthalpy flux. U plus P is enthalpy density. And so we could derive a combined equation for total energy density, thermal fluid, and if we included an energy equation for the thermal fluid, we would find that this term is canceled. So there would be a UG dot grad PC, and then there would be a minus UG dot grad PC. It would go away. And we'd be left with d by dt, partial T, of the total energy density of the combined thermal and cosmic ray gas would be the divergence of an enthalpy flux and kinetic energy flux. So it would all be very nice. And we're not going to go that far, but we could do it. Okay. So now we have enough of a fluid description of cosmic rays to include in a model. And the astrophysical literature abounds with these treatments. Okay. But there's another transport theory, and it goes back all the way to the, not quite as far back as Parker, but to the late 1960s, the late 60s and the early 70s. So let me tell you a little bit about that. Say what? The disco era. The disco. These are two of the most non-disco people that I can imagine. I cannot imagine any of them. Well, maybe the only part staying alive. Okay, they've done really well with that. So Parker made it to 94. Russell Pulsrud is well into his 90s. And I think Don Wenzel is still on the planet. Okay, so maybe they are appropriate for the disco era. Okay. Wow, there's actually a young person who understands that. Okay, so now we're going to get to this alternative model. Cosmic ray self-confinement. Okay. The conclusion, so what I'm going to do is I'm going to tell you what it leads to, and then I'm going to show you a little bit about where it comes from. So let's call it the conclusion of the alternative model. We're going to replace UG in the Parker transport equation by another velocity, UG, plus the so-called Alfvén velocity, VA. VA is named for Hans Alfvén. I think it goes this way. And it's B divided by 4 pi mass density. So what does this mean? What is the Alfvén velocity? Well, if we start with a straight field line and we kind of pluck it, so we make a little perturbation of it like so, there'll be a magnetic tension force that's associated. So we're always invited to think of magnetic field lines as kind of elastic strings. And so if you pluck it, it wants to straighten out. So there's a tension force. And that tension force, of course, will overshoot. And so go like so, and it will split and it will lead to waves propagating away in both directions. And the speed of those tension-driven waves wave speed is VA. So the scattering waves that we've talked about, these fluctuations that are scattering the cosmic rays, we can kind of think of them as Alfvén waves. So I've been impressed in the past couple of days by how many of you have asked me in one form or another, okay, but what's the effect of cosmic rays transferring momentum to the waves? So you're being good physicists. You should always follow the energy. If you're in finance, you follow the money. If you're in physics, you should follow the energy. And now it's time to ask what happens to that energy and momentum that is transferred from cosmic rays to waves. So what we do is we define a wave frame. So it's moving with the fluid, U gas plus VA. And if cosmic rays are streaming relative to that frame, they can amplify the waves. So our picture would be this. Here's our field line. Here's our wave frame. If the cosmic rays have a velocity we just call it CR, and isotropy like so. So the cosmic rays have a positive momentum in the frame of the waves, and they transfer some of that momentum to the waves, and that allows them to grow. They transfer momentum and energy. If the waves were moving the other way, they would have negative momentum. Cosmic rays would, the only momentum they could add to them would be positive momentum, which would reduce the magnitude of their momentum, which would damp them. And we know from our previous work that if there is a lot of scattering, the anisotropy is equivalent to streaming down the density gradient, or the cosmic ray density gradient. So the criterion for instability so L-phase waves are amplified if the cosmic rays have a positive anisotropy in their frame. And there's a nice kinetic theory of this. And there are many places you can see it. You can see it in Kulsrud's 2005 book. And you can see it in my review paper in Physics of Plasmas in 2017. I go through this, and actually a lot of what we've been doing these past 3 days in that, and I think I put that, I meant to put that on the Slack references. If it's not there, I'll put it there. But we're not going to do the kinetic theory of this because that would be, a whole hour and a half in itself. But I will tell you the growth rate. So gamma is a constant of order unity times the number density of cosmic rays divided by the number density of ions. times the cyclotron frequency times the relative anisotropy in the frame of the waves. It can be written like this: V drift over VA minus 1. This is a tiny number. So this is about maybe 10 to the minus 9. This in the interstellar medium is a moderately tiny number. It's about 10 to the minus 2. So gamma is order typically 10 to the minus 11 per second. That seems like a long time, but in astrophysical terms, it's actually short. So, and especially if the drift velocity is much larger than the Alfvén speed. So the assumption, and this assumption is actually just beginning to be tested by numerical simulations. And so far it's holding up, but it's a pretty limited set of calculations so far. So the assumption is that the instability saturates by providing enough scattering to keep the cosmic rays near marginal stability. Which is Alfvén extreming. Okay. And therefore, the cosmic ray fluid moves at VA relative to the gas. Okay. Oh, sorry. Yeah, please. It is, yeah, so that's an interesting question. So the mean-free path is about the scattering mean-free path from observations is about 1 parsec. And it turns out that delta B over B of order 10 to the minus 3 is enough to give you a mean-free path of about a parsec. And so there actually is a nonlinear damping mechanism called nonlinear Landau damping. And what it is that there's an effectively a wave pressure associated with these fluctuations, and thermal plasma, mostly thermal ions, can absorb energy from the pressure force associated with this. That's kind of a simple physical description of it. But there are linear damping mechanisms as well, and which one is more important depends on the state of the medium, its temperature, its density, and so on. Yeah. It's yeah, that's a great question. So it's actually a variant of Landau damping through the so-called gyro resonance. And so the Landau resonance, let me just say a little bit about both of them. So the Landau resonance occurs for particles moving at the same speed as the wave. And they're accelerated by the wave electric field. Parallel. So actually, okay, so that's the Landau resonance. The gyro resonance is when the Doppler shifted, so the wave frequency Doppler shifted to the particle frame is the same as the cyclotron frequency. So when that condition is satisfied, the wave, as it essentially sees a constant frequency of magnetic fields in its cyclotron motion, and this can lead to a net absorption or emission of energy. Good question. Okay. So we keep all the machinery that we developed for the Parker transport equation, namely the frequent scattering, the near isotropy, the ordering of 3 timescales, and we go through the same manipulations and we come up with an alternative energy equation. So our alternative energy equation, we just substitute UG plus VA for UG. I actually didn't realize this for a long time. I went through a lot of pain to derive it from first principles, but this actually works. So what is it? Partial UC, partial T, is minus the divergence of the enthalpy flux, UG plus VA, times UC plus PC. Okay. And then not only do we have to cancel out the extra UG dot grad PC, so this was the work term, but we have to do the same thing with the Alfvén speed. And this turns out to be a heating term. So you can show by direct calculation shows that this is the energy this is the energy transferred to the waves. And then in a steady state, the waves have got to give it to the plasma. So whereas the Parker theory showed that the cosmic rays could do work on the gas, it doesn't have heating. The self-confinement theory has heating. That is the main difference. And since, of course, temperature is not only very important for gas dynamics, but very important for diagnosing gas dynamics, this term is very consequential. Okay, and then we have our diffusion. And then we have our sources. Okay, so we have these two theories, and they're both, they're examples of both in the literature. My group has, worked quite a bit with both to try to understand their differences. So now I'd like to show you a little bit of where that goes. So this would be a great time to have the projector and the screen. So you're going to see this phrase popping up a lot. And that's because I give a lot of astronomy colloquia. So I reuse some slides. I give a lot of astronomy colloquia, and a lot of astronomers kind of have to be dragged into plasma physics, kicking and screaming. And so I like to kind of emphasize, rub their nose in the moral of the story, which is that you cannot avoid doing plasma physics sometimes if you want to have secure astronomical predictions. So this is going to appear a lot. Okay. So I want to show you one more thing before embarking on this whole set of slides. Actually, let me just show it to you. Well, okay, that's actually the second one. Okay, so this is an analytic solution, steady state version of this equation with diffusion, no gas velocity, alphane velocity, and a delta function source at the origin. And I've included it because I wanted to show you the kind of the different behaviors you get when you're diffusion dominated versus when you're streaming dominated. So you can solve that model analytically. S naught is the strength of the source. Gamma here is 4/3 for a relativistic fluid, so that's just a numerical factor. And this is a problem. So just to sketch the problem, here's the x-axis, and we have L, and we have minus L, and we have a delta function source of strength S naught, and we look for a steady state solution that vanishes at the boundaries, plus and minus L. That's easy to solve. And here are 3 different examples for 3 different diffusivities. And you can see that when the diffusivity is rather small, you basically get a kind of flat profile, which is then forced to go to 0 at the boundary. As you increase the diffusion, so this is the case with the largest diffusivity, first, so you notice a couple things. First of all, the cosmic ray pressure is much lower in this solution near the origin than it is in this one, and that's because you have very fast transport. You have a lot of diffusion. You have a relatively small pressure gradient, and you have basically a linear behavior. And then this blue solution is sort of intermediate. So depending on whether streaming dominates or diffusion dominates, you get very different behavior from this very simple problem. Now, the picture with actually weak diffusion or zero diffusion. So the zero diffusion streaming picture actually carries the seeds of its own demise. And how does that happen? If you set partial t, UG, and kappa identically equal to 0, you can show, well, so what does that say? That says that the cosmic rays are basically carried at the Alfvén speed, and if VA decreases, because the gas density increases, well, that's just kind of a standard equation of continuity effect. You're being carried along at the Alfvén speed. The Alfvén speed is going down, so the density must go up. Okay, so if the gas density increases, then the cosmic ray pressure increases too. If the cosmic ray pressure increases, according to our theory, that should reverse the direction of streaming. And the waves get reabsorbed. So the first person who thought about this, or at least thought about it in print, was John Skilling in the early 1970s. And his conjecture, which he didn't really show, was that this was just an irreconcilable situation. You know, the cosmic rays are trapped, they're moving down their density gradient, their own pressure gradient. Suddenly the density, the plasma density goes up. That means their gradient reverses. So he said there's just no reconciliation of this. What will happen is that the cosmic ray pressure goes flat. And shortly thereafter, he left the field and became one of the early developers of maximum entropy theory and made an enormous amount of money consulting for police departments and various security agencies. No more contributions to cosmic ray astrophysics. And it took until 2017 for Josh Wiener, postdoc in my group, to numerically demonstrate this effect for the first time, which he did in a one-dimensional model. What have I done with, here's the pointer. So this is a model where cosmic rays are injected here, and there's a small negative density gradient in the medium. And so here are some different times. The initial condition, blue curve is after 1.5 million years. The red curve is 3 mega years, 4.5, 6. And so what happens is that this cosmic ray front kind of moves, eventually adopts this profile. And there's an invariant in the system, which is that when everything is nice and the cosmic rays are trapped, that P cosmic ray is proportional to the gas density to the gamma over 2, which is rho gas to the 2/3. So if the gas density is an increasing function of position, the cosmic ray pressure will go up in the same proportion. And what this shows is that after the profile has relaxed, this invariant is pretty well obeyed. Then we put a cloud in one dimension, showed by this increase in density. So it's just a simple Gaussian profile. It leads to this dip in the alphane speed. And what you can see is that between the maximum in the density and the source, the cosmic ray pressure just goes flat. Then when the density starts to decrease, there's a huge drop in cosmic ray pressure. The cosmic rays re-engage, and they approach something that looks a little bit like this. So in here, there are no waves. There's no work done on the fluid by the cosmic rays, and there's no heating. Okay, that's what I mean by the system carrying the seeds of its own demise. The buildup of cosmic ray pressure behind the front or behind the density maximum can actually accelerate the cloud, and the heating here where the cosmic rays re-engage can kind of ablate the cloud, heat it up and destroy it. And we've done a lot of numerical experiments on this, including most recently the propagation of cosmic rays, now the source is on the bottom, into a medium with density clumps. And you can see that you get this very irregular propagation. And I don't know if you can see very well, but the magnetic field lines are quite distorted here. So this alphanic streaming picture leads to some somewhat freaky looking results. Now, what about the contrast between these two transport models, the self-confinement model and the Parker model? So here are two snapshots for two different models of how gas evolves and stars form in a galaxy. What we're visualizing here is the tracer in both cases is the gas density. This is, okay, so look at the scale here. A kiloparsec is about 3,000 light years. So this is an enormous box. Here is a newly formed galaxy, and the yellow is where the gas is densest, and we have a prescription. So where the gas is dense, stars form, the stars explode as supernovae, some of their energy goes into cosmic rays. We talked about this on the first day, but the cosmic rays remain kind of stuck and frozen to the gas. So this is based on the Parker model. And so what happens is they add some pressure to the disk and puff it up, but nothing much happens. If we allow them to stream at the alphane speed, they get away from the densest gas and phew, they drive this huge galactic wind. So it's a big difference. It's a big difference which model is right. Now, when we came up with this result, I actually got very nervous because what we have here is a situation where this relativistic fluid with essentially zero inertia is supporting a thermal gas against gravity. This sounds like a Rayleigh-Taylor instability, right? A light fluid holding up a heavy fluid. And in astrophysics, this has a name, not the Rayleigh-Taylor instability. Let me skip this. So these are showing the effect on the star formation rate. Let me just focus on the instability. So this is another of Gene Parker's contributions, again from the mid-1960s. And he said, well, okay, so suppose you have gas which is held up above its natural scale height by cosmic ray pressure and also magnetic pressure. So there's some free energy in the system, which is the gravitational potential energy of thermal gas held up above its natural scale height. So if you can make an undular perturbation of the magnetic field lines, gas would just kind of slide down into these valleys, releasing potential energy, and this would be an unstable situation. And then here, now that these field lines have gotten rid of their thermal gas, they'd just be free to rise, inflated by cosmic rays. So the free energy source of the instability is gravitational potential energy, but that gravitational potential energy must exceed the energy you have to expend to compress the gas in the valleys. So whether the system is really unstable boils down to whether to how compressible this thermal gas is. Now, critically, Parker did his work 3 years before any of these papers on the cosmic ray streaming instability were published. And actually, he had his own equation, but for some reason he didn't use it. So he made kind of a classic model where the gas pressure is mostly dynamical pressure. U here is some kind of turbulent velocity. Alpha is the ratio of magnetic pressure to thermal gas pressure, and it's assumed to be a constant. Beta is the ratio of cosmic ray pressure to gas pressure. This is the scale height in a constant gravitational field, so it's boosted by magnetic pressure and cosmic ray pressure. And what he showed is that for stability, the gamma for the gas has to be greater than this quantity. So he assumed that compressing the cosmic rays doesn't take any work. So that the cosmic rays are essentially a gamma equals 0 fluid. They're important for supporting the gas through this beta parameter, but they don't actually do anything. It doesn't take any work to compress them. And he said, well, gamma for the gas is actually 1 because the gas radiates very efficiently. And so the interstellar medium is always unstable. The magnetic field and cosmic rays are always trying to escape through this instability and making these pockets of interstellar clouds. Okay, so so this was a very influential. His original paper and the spin-off papers were very influential, and they left sort of an enduring message, which is that there's an upper limit to the fraction of hydrostatic support that can be provided to a gas layer by magnetic fields and cosmic rays through this Rayleigh-Taylor-like effect. But what that upper limit actually is depends critically on the compressibility of the interstellar medium. So, and I worked on this long ago as a grad student, but in the last few years, we've concentrated on putting modern cosmic ray transport physics into Parker. And here's what happens. So this is a plot. The color represents the growth rate. And because these numbers are kind of tiny, I've written the maximum growth rate in units of a free fall time and the maximum wave number in units of a scale height. So this is horizontal wave number in units of scale height going up to 1.4. This is vertical wave number. The fastest growing modes have a very long wavelength perpendicular to the direction of the magnetic field, which is the direction which is parallel to the galactic plane. And in these units, the maximum growth rate is 0.6, and the maximum wave number is 0.7. Now, modified Parker is the case without alphanic streaming, but with gamma for the cosmic rays being 4/3. So we added this additional stiffness to the equation of state, and you can see that the domain of instability has shrunk enormously. The maximum growth rate in the same units is now 0.01. So it's very close to 0. And the maximum wave number is smaller by a factor of 10. So it's a much longer wavelength perturbation. So going from gamma cosmic ray equals 0 to gamma cosmic ray equals 4/3 has an enormously stabilizing effect. What if we put in streaming? So here is just transport with the gas, gamma equals 4/3. So this is the same plot you saw before. When we put in streaming and heating, the growth rate actually is even bigger than it is for classic Parker, and the maximum wavelength, the wavelength of maximum instability is a little bit shorter. So here, cosmic ray transport is really mattering. We've done nonlinear simulations. This was a later paper. So this first paper was work with Evan Heinz, recently graduated PhD student. This is with Evan Heinz, Chad Bustard, and me, published a couple of years ago. And we found that if you give Parker enough time to really get going, it behaves pretty much as advertised. What it does is it kind of achieves a filtration of the thermal gas. The thermal gas kind of sinks down closer to the galactic plane, and the magnetic fields and cosmic rays occupy a thicker disk, which is basically what Parker said it would happen, but it takes about half a gig a year. So in an effort to speed things up, which I'm doing right now, a student who recently joined my group, Rourke Habiger, has been looking at localized injection. And so the idea here is we're really trying to isolate the effect of cosmic ray buoyancy. So what we do is we start with a stratified galactic disk that can be either stable or unstable to Parker. We're looking at all cases. Then we imagine injecting a whole lot of energy through a supernova or a multiple cluster of supernovae. And what does that do? So that injects cosmic rays. The cosmic rays stream away down the magnetic field lines. They push the gas with them. So some of the gas pressure and density is replaced by cosmic ray pressure, and the thing rises. And what we're interested to see is if isolating this process leads to faster results, and we don't know yet. So qualitatively, we're kind of seeing what we expected to see, but we don't know whether this will really have an effect on galactic structure faster than the Parker instability itself. But Rourke has just gotten a fellowship from NASA to carry this further. So we will. Okay, so what I've tried to do in these three talks is give you kind of a close-up view of how very large-scale phenomena in astrophysics depend on microphysics. And I chose, sort of the quirkiest microphysics that we have. So not ordinary gas kinetic theory, but how to construct a fluid theory for a collisionless, relativistic, power law energy distribution moving through diffuse thermal gas in a magnetic field. And I hope I've given you some of the flavor of how we do this and how it then prints through to astrophysical conclusions at the largest scale. So that's what I set out to do. I'm writing what will be so I have these notes, which I'll scan and put online, but I'm also writing a long document for this Verena summer school, and I'll put that up there too. And it also has many references. So I think we have time for some questions. Thank you.
I guess, would you expect it, especially if you have some of the shorter wavelength instability, would you actually be able to observe any consequences of that? I mean, is there something?
Oh, yeah.
A wrinkle and whatever.
So, yeah. So the biggest challenge is that there are so many things that, the interstellar medium is such a turbulent place. But I skipped over this slide, but it turns out that the most unstable Parker modes have a long wavelength parallel to the magnetic field, but a very short wavelength in the horizontal direction perpendicular to the magnetic field. And so we have done some calculations in 3 dimensions. In fact, all works calculations are in 3 dimensions. But this is what the Parker instability would look like observed in a galaxy that's seen face on. So this is a little piece of a galactic disk. And the 2 different colors represent different directions of the magnetic field coming out of the galactic plane. And this would be detected through Faraday rotation. So the idea is that if we looked now in the plane, that one of these Parker loops, so this, this side might be blue and this side might be yellow. So you would get this, sort of tweed rug type effect here. And Rainer Beck, who's a big galactic magnetic field radio astronomer, says, oh, we see galaxies that look like this. So I don't know. So maybe we're seeing Parker. Yeah.
Sorry, could you please summarize
Yeah, the conclusion of today's lecture is that we have 2 theories of cosmic ray transport, and they're both based on the assumption that the cosmic rays are frequently scattered by fluctuations that mostly just change their pitch angle. Very little energy change, but mostly a pitch angle change. And these 2 theories differ in the origin of these fluctuations. So in the classic Parker model, the fluctuations are just there. They're part of like a turbulent interstellar cascade or something. And in the self-confinement picture, the fluctuations are only the fluctuations which are destabilized by cosmic rays streaming. And so they lead to transport of the cosmic rays at a velocity which is equal to the gas velocity plus the speed of the waves, which is the Alfvén speed. And because these waves are being continuously excited by cosmic rays, in a steady state, the energy that's going into the waves from the cosmic rays must then be absorbed by the thermal gas. Otherwise, the waves would just keep, growing. And so the 2 theories have a very similar structure, but the one with wave growth includes a heating term. And then I showed that the predictions of the theories for both the Parker instability, for galactic winds, it turns out also the predicted star formation rates in the theories are very different. Really depends on which transport model you use. So it's very important to get it right, which means understanding interstellar turbulence and understanding this instability. Steve, and then actually let's call on the student first, if you don't mind. Yeah, go ahead. Sorry, I should have explained that more clearly. So the picture is basically this. So the galaxy is a thin disk, and then it's got this nuclear bulge. And so near the disk, gravity is pointing like so, and the magnetic field is predominantly parallel to the galactic plane. So the Parker instability is in a box like this. Is that clear? Great. Okay, Steve. Well, yeah, that's an interesting question. So actually, that's what I asked you about when I saw you this morning. So how effective these waves are in confining the cosmic rays depends on how effectively they're damped. So for example, in a medium with a lot of neutrals, it turns out there's strong ion neutral friction that's very effective. I mentioned this nonlinear Landau damping process in response to your question. And there's a third theory, which or proposed mechanism, which I think is the one that has the most in common with what you just said, and that is that these Alfvén waves really don't live on a uniform background magnetic field. They live on a background magnetic field that has its own turbulence. And what we think magnetohydrodynamic turbulence does is it produces kind of anisotropic fluctuations with a very short perpendicular wavelength. So it might be, maybe look a little bit like this. And so then an Alfvén wave traveling on a field line, down field lines, but a lot of this transverse structure would get sheared apart. And maybe that's a little bit like what you're talking about. Flow would probably do the same thing. If you had flows, so these waves are really, they're pretty small scale because this gyro resonant amplification mechanism picks out waves of wavelength of order the cosmic ray gyro radius, which is, sub-astronomical unit. So it kind of depends on what you think the interstellar turbulent cascade is doing. Yeah. Yeah. So there's been a decades-long quest to look at to detect the Parker instability in galaxies. And there've been a lot of false alarms, sort of loop-like structures that turned out to be, blown by clusters of supernovae and so on. I think that our best chance is in something like this. And maybe it already has been seen. There are a lot of observations of galactic winds now. And the critical difference between a cosmic ray driven wind of the kind I described and a wind that's driven in another way would be the temperature. The cosmic ray heating produces a much hotter medium than these other. So that would be another diagnostic. And what are some? There are no clear, unambiguous observations, I would say, of either one. And that's why we're trying to make the modeling as realistic as possible, really. Okay. Well, let's eat lunch. Thank you.